Hello, Narnach here. Welcome back to another episode of ShenZhen I. This episode we're gonna look at the puzzle Rubbish Audio Thing for the Harmonix Maximization Engine. So, as always, we're gonna start with email and then we're gonna go onwards to all the solutions. Up here you see I've managed to get a pretty decent set of solutions, so this is gonna get fun. So, Carl is a bit of an audio snob, so a contract comes in to build a piece of audio kit. Sounds fun, right? I've always liked audio. This client promises that their little box will deliver crisp highs and booming lows, all in perfect balance. Then I see their advert happens to include the much vaunted algorithm that powers the thing. Go on, take a look yourself. I should mention I put a copy of said advert on your desk. Just look in the pile of papers marked as supplemental data, since that seemed most appropriate. So we're gonna go over to the manual, because in the back of the manual is a section marked as supplemental data. And that is what we have here. I'm not gonna read the entire thing, because it is a bit of a long advert, but the key bit here is the algorithm. Audio out equals audio in minus 50 times 4 plus 50. That's the core optimization algorithm that they use. I've copied it into the puzzle so we don't have to keep it around. So let's go back. I should also mention that we still have to do this. As sad as it is, work and all, even when you have to help a dodgy American company make rubbish like this as premium kit for audio files. So we have a series of optimizations here, because you can do a lot of things with this. So first of all, the algorithm. One of the first things I noticed was that it does more steps than you really should if you do the math. So audio out equals audio in minus 50 times 4 plus 50. So if you write that out, then you can say, okay, this is 4 times in minus 4 times 50, which is 200 plus 50. So if you write that out even further, we get to 4 times in minus 150. So this is only 2 operations, while here you have a couple more operations. So simplifying the math to its most fundamental steps will help you write less code, and of course no code is faster than no code. So let's jump to a implementation. This one, we have a maximize button, which is gonna send a 0 if it's not maximized, and it's gonna send a 1 if we need to maximize it. So we don't always do it, we have to selectively do it. So when this is a 0, we just pass in the original value and we just pass it out. When we maximize it, we are going to change the output value. So what we do here is we test if port 1, the maximize button, if it's equal to 100. Basically we test are we maximizing? If so, we jump to max. Otherwise, we simply take the original audio, which comes in on port 0, and we pass it out to X3. Ideally, there would be a component that has an extra analog output, so we can just pass it straight through. In this case, we have 2 analog inputs, that's what we connect, so all we have is digital or the XBus outputs. So that's exactly what we use here. So the output goes here. We send it through, and all we do here is we take the output or the input on XBus and we pass it out on a analog signal. So this is a digital to analog converter for $3. It's way expensive for what it does, but it's what we do. Later on, we're gonna optimize this in a different way. So when we're not maximizing, that's all we do. We take the signal, we pass it through, we sleep, and we jump back to the test. Okay, so what if the test is true? What if we need to optimize it? So then we take the input value, in from port 0, and we put it in the accumulator. So that's where we do all operations. So the first thing we need to do is multiply it by 4. So that's what we do. We multiply it by 4. So we take the value in accumulator, multiply it by 4, and it writes back. Multiply is very nice that way. Similarly, subtract also works in place. So then we subtract 150 from this value. And then whatever value is left, we send it out via X3. That's the same as when it would have come true. And then after that, we sleep and we test again. So This is a rather straightforward solution, and indeed it works as advertised. Problem is we are using a big 5 yen component and a 3 yen component, so we can optimize this a bit. Also, we are using quite a bunch of power, and there are more optimal solutions. So the first step was to see, can we cram this into slightly smaller components? So can we use 2 of the 3 yen components? In order to do that, we needed to change the logic here a little bit, but it still works. The trade-off is going to be that we use slightly more power. So normally we check, do we have a maximized signal or not? And then based on that, we do one or the other. Because we have to condense the instructions that we use, what we're instead doing is we're trying to streamline the process as much as possible, trying to find similarities and areas where we can reuse code. So both of the steps, whether we are maximizing or not, they need the input value and something needs to be written to the output. So that's what we're combining here. Both are going to use the accumulator. So the very first step is not checking whether we need to maximize or not. We are just taking the input and we're storing it in the accumulator. After that, we're going to check, are we maximizing or not? If we are not, we're going to jump to the flush. If we are maximizing, we're jumping to the maximizing instruction. Actually, we don't need to do that. All we need to do here is check, do we need to maximize? If it's not the case, we jump to the output. If it is, we will just skip this jump and we instantly fall through to maximize. So just optimizing the order in which you put your jump statements does help you to optimize your code. So in this case, we multiply the accumulator by 4 and then subtract 150. And then after that, we fall into the flush, which sends the output out, and then we sleep for 1 second and then we loop back again. So this will always do the same thing. And here we still have our digital to analog converter because we're still bound by the number of ports, but the code is more compact, so we can fit it into a smaller box, and it only costs us 6 yen rather than 8. So the power usage is now going to go slightly down compared to the reference because we have 1 less jump in here. But as you see, we're still stuck in this huge middle section of just very popular solutions. So let's improve things further. We're going to use an energy efficient digital analog converter. Say hello to our little friend, the DX300. We last episode already explained to you how it worked. If you put a digital signal on the digital one, it would split it out into analog. But it also works in reverse. So you got this nice reverse button up top here. And that allows you to work it in reverse. So we now have an input on the analog side and it sends out digital signals. And that way, on the input side, we can use a digital input and an analog input. And then we still have a analog output available. So we only use one of the microcomputers rather than needing a second one as a digital analog converter. So the specific ports I'm using here is relevant. So the input signal is going to be either a 1 or a 0, indicating it's on or off. So if you connect this one to P2, this one maps to the 100 range. So if this is on, it's going to send a value of 100 out. If you connect it in the middle one, it's going to send a value of 10 out. If you connect it to the top one, it's going to send a value of 1. In this case, because of how things are fitting here, I figured it would be nicer to do it this way. So we have to check whether we get a value of 100, and in that case it's on. That's the same as before, so most of the logic still stands. So we test if we have a value, and then we jump to max, and it's all the same from there. And in this case, we use a lot less power, 326 power to be precise. And because we use the large module, because we have enough instructions, are costing 6 yen here. So then we're gonna optimize a bit further, make it cheaper at the expense of power. So the DX300 is still in here, but we used a slightly more efficient power loop. Also, we just realized that we don't actually need that jump instruction, so this should be even better now. Might actually be on par. So we're using 329 power. As the highest. I mean, depending on how long we're maximizing, things are different. So we optimized it even further, but we're still in this small valley here, and there is a better solution, and a lot of people have found it. So onwards we go. Can we optimize it even further? So one of the things I was looking at is, can we inline our loops? So we're back to the large code, but one of the things that we did, actually compare it to this one. Yes, here. So what we do here is, let's say we're not maximizing. So we test, we're not maximizing, so we skip the jump. Then we send the value straight through. We sleep for a second and we jump back to the test. This jump is executed every single time. And then we do the test. And if the test is true, then we jump over to max. But what if we inlined the test code? This is a technique I picked it up in the TS 100, where sometimes if you have a very small loop with a test and then some instructions, and the test doesn't jump to something that you have afterwards, what you can do is, rather than here, because this used to be the jump to test, these two lines, they used to be the jump to test. So what we did instead is we took the test that we're applying up here, test of equal to 100, and if that's not the case, we jump back. If it is the case, we go to max. So because we have the space in this rather large component, we can use that to our advantage to take out a jump and make the code more efficient. And the result, of course, is that the code runs a tiny bit faster. 322 power in the least efficient run. And some of them are slightly better because, as I said, how long the code runs. But we're still in this valley. So, but again, this got me thinking. We're doing some conditional jumping, but what if we actually didn't have any jumping at all? So, one test. Because we only need to test once. Are we maximizing or not? If we are maximizing, we send the input value, we send it straight out, and then we sleep. If we are maximizing, then we take the input, we store it, we apply the operations, and we send it out. But because we only have a single test, we can use multiple plus and minus signs to separate all the cases. And that will allow us to take out all the intermittent jumps and only do the test and go and get to one of the most efficient forms of the code possible. So we test if we are maximizing. If that's not the case, then we send out the value. Then, of course, I can actually show you. So we test. We don't have 0, so we send the value out. And then we just skip over all the other code and we sleep. And we go back. We do that a couple of times. And we barely use any power. And then we get to where we start maximizing. So now the test is true. The first statement is not executed, and now we get to the maximization code. We send the value to the accumulator, we multiply, we subtract, we send the accumulator out, and then we fall through to the sleep. And we do the test again. And this is gonna repeat until we stop maximizing. And then the test is executed. It flips whether the pluses or the minuses are active. and we only do the efficient bit. And there's no longer any intermittent jumping. And as far as I am aware, you can't get more efficient than this. Because these are all just required components. There you have it. And of course, our colleague Joe. Holy crap, that thing is awesome. I hooked one of these babies up to my stereo at home and it blew the speakers clear off. Does the job, no question. Amazing. So that is one happy customer. So as always, I'm gonna thank you very much for watching. If you do manage to find a way to do it even better and use different components, whatever, please do leave a comment below. And if not, just look forward to the next episode. Until then, I'm gonna thank you very much for watching, and I'll see you again next time. Bye bye.